Okay, so we continue on with chapter 8. And now we're going to look at types of reactions. So there are actually 4 different types of reactions we're going to look at. So 4 types. The 4 types are combination reactions. We're going to look at each one of these in detail. So combination reactions, decomposition reactions, and then we're going to have single displacement reactions. Displacement or replacement mean exactly the same thing. And double displacement or replacement reactions. So those are the 4 different types of reactions we're going to look at in chapter 8. So okay, if we let's start with combination reactions. Now your book goes through several different types of combination reactions, and no, you do not have to memorize each type of reaction. That's a lot. So we're going to focus on sort of the main ones, but what in general do we talk about with combination reactions? Combination reactions means you take some compound, or you take something A plus something B and you get AB. And sometimes you get plus CD. Sometimes you make more than one product out of that deal, but in general you're going to make, that's a goofy looking B. My apologies, it just bugs me. Alright, I guess that's not so much better, but anyway. So you take 2 things, 2 or more things, you put them together and you make something else. And that's a combination reaction. The one that we're going to see most often is what we call a combustion reaction. This is important. This is how your car works. You have a combustion engine because it uses a combustion reaction to produce heat or produce the energy that moves your car. Guess what? Your body works the same way. Your body works by using combustion reactions. Your body takes carbohydrates or sugars and reacts them with oxygen to produce heat or other type of energy that makes you function. This is why we eat. This is why energy is predominantly comes from carbohydrates, because the carbohydrates are combustible. They react with oxygen. So when we look at a combination or a combustion reaction, what is that? Remember, a combustion reaction is a special type of combination reaction. It's the only combination reaction that I'm going to specifically hold you accountable for. Okay, so this is a reaction you have to be able to recognize and know what to do with, and know what those reactants and products are. So, and we've seen this before. We did this in Lab 3 and in Lab 4. So the generic form of combustion reaction is you take a hydrocarbon, I'll explain what a hydrocarbon is in a second, plus O2 gas, and you're always going to get carbon dioxide plus water. Now the water, depending on the situation, could be in the gas form or the liquid form. Depends on the situation. In your body, it's going to be in the liquid form. In your engine, probably more likely going to be in the gas form. Okay, it may condense to form a liquid. It just depends on the temperature of the reaction in the big scheme of things. So that gets a little wishy-washy. But what the heck is a hydrocarbon? A hydrocarbon just means it's a compound containing carbon and hydrogen. It may contain oxygen or may also contain oxygen, nitrogen, sulfur, but it will for sure have carbons and hydrogens. Gasoline is nothing but carbons and hydrogens. If you talk about ethanol being in the gasoline, ethanol has oxygen in it. If you talk about sugars, carbohydrates are nothing but carbons, hydrogens, and oxygens. That's a hydrocarbon. Reacts with oxygen gas and produces carbon dioxide and water, and you also get heat out of the deal. Okay, that's why we run these, because technically speaking, you also produce heat. And we'll talk about later at the end of this chapter, we'll talk about that heat component. But for right now, the fact that hydrocarbon plus O2 gas produces CO2 gas and water is important. So if we look at an example of that, say we have, and don't forget we have to balance, so say we have a gasoline, we have C4H10 as a gas. It's not octane. Octane is C8, but it can be used not as a gasoline, but it's a hydrocarbon. Remember, by definition, combustion means we have to react with oxygen. And we're always going to make CO2 gas plus H2O, either gas or liquid. Again, it depends on the reaction. I'm not going to be picky about whether you use the water in a gas form or a liquid form. I'm not picky about that, but the CO2 is in the gas form. Okay, that's going to be important. So here's our combustion reaction. We have our hydrocarbon. We react it with oxygen. We make CO2 and water. We have to balance this guy. Okay, well, let's do an account of everything. Where are we at? So we have carbons, hydrogens, and oxygens. That's all we got. So what do we have here? We have 4 carbons on the reactant side, 10 hydrogens, 2 oxygens. Product side, we have 1 carbon, 2 hydrogens, 3 oxygens total. We have 2 in the carbon dioxide, 1 in the water. We are not balanced here. Alright, well, let's go through our process. Okay, so if we go through our process, I'm just going to rewrite this to make this a little clearer to go through this process. So we have our C4H10 gas plus our O2 gas gives us our CO2 gas plus H2O gas. Okay, so remember our process. We start with, do we have any metals? Nope, no metals. Okay, well, that's easy. Done. Check. Now we move on to nonmetals, everything but hydrogen and oxygen. So that leaves us with carbon. Alright, so if we look at carbon on the reactant side, we have 4 carbons. Product side, we have 1. So if we put a 4 here, now we have 4 carbons on the reactant side, 4 carbons on the product side. We're good to go there. Fantastic. Okay, now we move on to hydrogen. On the reactant side, we have 10 hydrogens. Product side, we have 2 hydrogens. So how are we going to balance that? With a good old 5 here. 5 times 2 is 10. So now we have 10 hydrogens on the product side, 10 hydrogens on the reactant side. Okay, we're almost done. All that's left is oxygen. Okay, so we have 2 oxygens on the reactant side. Product side, we have 4 times 2 oxygens in the carbon dioxide. That's 8. 5 times 1 is 5. So we have 8 plus 5 is 13. Well, we have an odd number, so we have 13 oxygens here and 2 oxygens here. Well, what on earth are we going to do with that? How are we going to put a coefficient in front of that O2? This is what I meant when I said that oxygen can kind of be a pain in the butt. Because you can't have half of an oxygen atom. So how are we going to get an odd number of oxygens on the reactant side? Guess what? We can't have an odd number of oxygens on the reactant side. So how do we deal with that? Well, that means we're basically going to have to go through and multiply everything by 2. A way of thinking about this is, as we stand, the only way to make this match up is if we had 13 halves here. If we had 13 halves of O2, then we'd have our 13 oxygens. But guess what? We can't have a fraction as a coefficient. That is not okay. Okay. It's very important that we don't have a fraction. So how do we get rid of that fraction? Well, I'm going to rewrite this, and we simply have to multiply everything through by 2 to get rid of that fraction. So I'm going to rewrite this. So now I'm going to go through and multiply all those coefficients that are up there by 2. So that means we have 2 times 1 is 2. 13 halves times 2 is 13. 4 times 2 is 8. 5 times 2 is 10. Now let's look at this. So again, we have carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. How many carbons do we have? Well, now we've got 2 times 4 is 8. 2 times 10 is 20 hydrogens, and 13 times 2 is 26 oxygens. We go over to the product side. We have 8 carbons. 10 times 2 is 20 hydrogens, and we have 8 times 2 is 16, and 10 times 1 is 10, so 16 plus 10 is 26 oxygens. Now we're balanced. Okay. We have to have whole number coefficients in front. We always have to have that. We also have to have the lowest possible number coefficients. So you want to be careful with that. Okay, that's important to understand. This is where I said the oxygen can really throw you a curveball. So you got to be careful with that. If you don't understand how I got from the top equation down to that second equation, ask. Okay, like I said, the oxygens can be goofy. At the end of the day, you have to have whole number coefficients, and you have to have the same number of atoms on both sides. And the coefficients have to be in their lowest possible number. Whole number is important. Okay, so that's combination reactions. Like I said, the combustion reaction is the only combination reaction that I'm going to hold you accountable for. We'll still see other combination reactions. You have to be able to recognize that something's a combination reaction. But knowing those specific ones, no. Okay, those other specific ones that your book goes through, you don't have to know those. Just the combustion is the big one. So then if we move on to decomposition reactions, decomposition reactions basically are just the opposite of combination reactions. So decomposition reactions, what happens? Well, you have some compound and it breaks up into A plus B. It splits apart. It decomposes. Oftentimes heat's involved. That's the other component, the other symbol that we didn't talk about. Sometimes you'll see this little triangle. This little triangle means heat. When you see that over an arrow in a chemical reaction, it just means heat was involved. Heat was applied to that system, which helped it decompose. And that's something that's important that you'll see and understand. So what's an example of that? So your book goes through a couple of those. The one that we're going to look at and think about is the fact that carbonates and hydrogen carbonates do this. They actually decompose. They decompose to produce CO2 gas. So an example of that is if you had carbonic acid, and you're going to see this again when we talk about equilibrium. We're going to see carbonic acid again because it's actually a very important component in our blood. Okay, so we'll talk about blood pH and we'll talk about equilibrium. That's chapter 16, so don't panic yet. But what can happen is carbonic acid can actually decompose into CO2 gas plus H2O liquid. And this happens naturally. You actually don't even need heat to do this. This happens naturally. So we see this often. So it's something you want to make sure to think about. Okay, again, we'll see this. We got to check to see if it's balanced. Let's see, we have two hydrogens on, start from scratch. We have one carbon on the reactant side, one carbon on product side. That's good. Two hydrogens on the reactant side, two hydrogens on the product side. That's good. 3 oxygens on the reactant side, 3 oxygens on the product side. Everything's already balanced. We're good to go. Okay. So that's something that we typically see most often. Again, you have to be able to recognize a decomposition reaction. Just start with something and it breaks into pieces. Okay, so not too bad. Another one that we've seen already in lab, if you recall, we had this following reaction. Remember we had the hydrogen peroxide, that was a liquid, and it broke down into water and oxygen gas. Remember that's the lab that we did. That's a decomposition reaction. And if we look at that, is it balanced? You should be shaking your head no. We have 2 hydrogens on the reactant side, 2 hydrogens on the product side. That's fine. We have 2 oxygens on the reactant side, 3 oxygens on the product side. Wah, wah, wah. What do we do with that? Well, we're going to go ahead and, what if we put a 2 there? Now what does that mean? We have 4 hydrogens. So now we got to put a 2 there, so we have 4 hydrogens on that side as well. Now we have 4 oxygens on the reactant side. We have 2 times 1 is 2, and 2 plus 2 is 4 oxygens on the product side. Now we're balanced. Okay, so those are 2 types of the 4 reactions that we'll see. The next one we're going to look at is single replacement reactions, and that one gets a little trickier because now we're going to have to figure out, does a reaction even happen or not? And we're going to have to look at the rules for that. And then the last one we'll look at is double displacement reactions, and then we'll look at that heat component when we produce heat in that stance. So that's it for combination reactions and decomposition reactions. Next up will be single replacement reactions.